Hello, everyone. To start our industry talk of today, I would like to welcome for today's session of the GLASE Industry Talks series. And our talk today is about power supplies and power distribution options for CEA operations. The GLASE Industry Talks is a series of informal conversations with academics and field experts about topics suggested by our industry members. These discussions provide the GLASE members an opportunity to learn more about their topics of interest and to connect with field experts. I would like to introduce today's presenters, Bahram Barzideh, from Principal Engineer of LED Lighting Components at Underwriters Laboratories, or UL, like everybody knows, and Frank Cirolia. He's a System and Application Engineer at Artesyn Embedded Technologies. Today's presentation will be divided into three sections. The first part, we're going to hear about power supplies, which will be presented by Bahram from UL. At the second part, we're going to talk and listen about DC power distribution applications in CEA systems, which will be presented by Frank from Artesyn. And then on the last part, we'll have 20 minutes for our discussion. As we did on the first industry talk, this is an informal conversation, really targeted to give the members an opportunity to ask questions and talk about those topics. So let's see if we can take advantage of this topic today. A recorded version of this webinar will be available at our website afterwards. You can also find the previous talk from phenolics, impacts of LED on plant phenolics production from Kevin Folta. That was our first industry talk. And I would like to give you a heads up about our next industry talk. We're going to be talking about the CEA market trends and analysis of the 2017 USDA Census of Agriculture. If you have any questions about the presentation or if you would like to get in contact with the speakers, please submit your inquiries using the chat box. You can also send me an email afterwards and I can make the connections between you and the speakers today. We'll do our best to answer your questions, and I hope you like our presentation today. So now, with no further ado, I would like to pass the word to Bahram. He will start the presentation talking about power supplies. Bahram, you are unmuted, and I'll stop sharing my screen. Please let me know if you can share yours.
Hello, everyone. This is Bahram Barzideh. Just want to confirm if everybody can see my screen.
Yes, we can.
Okay. Thank you very much for this opportunity to give this talk about LED drivers. A little bit about myself. My name is Bahram Barzideh. I'm with Underwriters Laboratories. I work in a small group at UL. We have the responsibility to maintain the various UL standards that UL manages on behalf of ANSI. That's one of our jobs. The standard I manage is UL 8750, which is really LED components for lighting purposes. So with that, let me get started. Erico had sent me several questions, and I have fashioned this conversation around these questions. As we go through the presentation, I will attempt to provide the answers to the questions that Erico had brought up. Before we get going, I wanted to let you know that I have nothing to sell. And throughout this presentation, you will see a lot of different types of equipment. In many cases, you will see the names of the manufacturer. I'm using these images to depict the items that I'm discussing. This is not an endorsement of one brand over another. I'm simply using it for our presentation purposes. So with that, let's get started. I wanted to look into, get started with a typical LED light bulb that you might buy at the store. This is a cutout of it. It has a lot of mechanical pieces. We are not going to focus on those things today. I am going to focus on two pieces inside the LED light bulb. There is this piece here with a little green background. This is called an LED driver. And this gray round piece on top, that's called an LED array. The job of the LED driver is to convert the branch circuit supply, in this case 120 volts, to the power levels that are necessary to properly operate this array. So let's say it's 120 volts, and let's say this array works at 12 volts DC at 350 milliamps. So that's what this device does. It converts one type of supply to another. The LED array obviously is the part that has LED packages on them. And these packages, when you apply the proper type of supply to them, they will emit photons and they create light. So those are the two fundamental elements for an LED lighting system, the driver and the array. Now, there is a similarity here between what it takes to build an LED luminaire or LED light and what you might be familiar with in your office, a basic fluorescent light. The fluorescent light also has two main parts. It has something called the ballast, which is similar in function to the LED driver in that it converts one type of supply to another type as needed for the light bulb to work. However, there is a substantial difference at the next step. If you go to your regular big box store, you will finally find a section where there is maybe 10 or 15 types of ballasts that correspond with specific types of fluorescent bulbs, meaning there is a limited number of the types of light sources that you can use for a fluorescent system. Over time, that lighting system has matured to a point where there is some correlation between the types of light sources and the types of ballasts. That is not true in LED lighting today. We have many manufacturers with many ideas about what type of supply they want to use, what they want to convert the branch circuit to, what type of LED arrays they will design, and what they want to do with those arrays as far as power ratings and whatnot. So there is literally an unknown number of permutations of drivers with ratings and arrays with ratings, which makes life very difficult for someone who is putting an LED luminaire together. They need to make sure that all these pieces actually correctly fit. So as part of this presentation, I'm going to talk about all the different types of differences, but just please keep in mind this basic difference that I have explained here. Now, what makes the LED light? It's basically a die. And this integrated circuit, when you apply the proper supply across it, it emits photons and you can see light. Now, the importance of this graph here is that LED lights are current dependent. They're not voltage dependent. The amount of power they put out has to do with how much current is applied across them. This makes it a very different type of a supply, needing a different type of supply as compared to other types of electrical devices that you might be familiar with. Your basic laptop also has a power supply where it converts one type of branch circuit supply to a certain voltage and current, but your laptop works on a constant voltage concept. LED packages require constant current. In other words, when you are designing an LED driver, it is of paramount importance that you have very good control over the amount of current that's available at the output, which is a little bit different from, you know, what you might see in many other utilization equipment, but that's the thing that makes LED drivers different. Now, this picture is basically one die inside a specific type of package. These are called chip on board. Very likely inside here is more than one die. So the voltage that's required across the terminals here, the amount of current that's necessary, each of these may be a different rating based on how it was designed. So in short, LED drivers, they provide a well-regulated power to drive the LEDs. Almost always, they should have a constant current source that will lead to good regulation, good operation of the circuit. There are low-end products in the market where manufacturers use constant voltage designs, or they are doing other things that make using a constant voltage design acceptable. But in most cases, they will be a constant current device. Because of the multitude of design possibilities, you can have some very simple designs, and I will show some, and you can have really complicated designs. A lot of the newer LED drivers also will have some sort of an interface to control them. Say, you know, you want to change the color temperature, you want to dim it out, or whatever that you want to do with that light, you will have some sort of a control. So this is another example of an implementation of an LED light. In this implementation, you have on one printed wiring board the LED driver. It connects to electricity right here, and here's the LED packages. So it's all in one, and that's just so that I apologize. That's just so that you can see that there are possibilities here. LED drivers come in different shapes and sizes. This, as you can see, is a ballast footprint. Many LED drivers will look like this because the lighting industry wanted to use essentially the same footprint for these types of drivers. Sometimes they go inside other things, so it's just a printed wiring board. This is a direct plug-in that happens to be an LED driver, and this is a remote device. So just to show that they can come in many sizes and shapes. Here's a very simple design. You have branch circuit, a little voltage divider, a diode pack, and the drivers, and that's it. So it's a very simple design, and likely not constant current. This is something a little bit more complicated. This is a switching design. This design does not have isolation, so the 36 volt that's out here is not isolated by a transformer or galvanically from the branch circuit. It's controlled by this chip. So obviously the regulation here at the output is a lot more controlled. Here's another design, very similar. This is also a switching supply. The difference here is that you have an isolation transformer. Also note this capacitor here that bridges between primary and secondary, and also this capacitor here. We'll talk about that for a minute, a little bit later. So remote drivers, these are drivers that are not in the same location or inside the same LED fixture. They are located remote. They can be in an attic, they can be in an equipment closet. They connect directly to branch circuit in some way. Normally, they will have their own appropriate fire and electrical enclosure. Or you can have drivers that might sit inside the luminaire itself. I am showing two versions of these. They might or might not have their own fire and electrical barrier, and they get connected to branch circuit with leads inside the equipment. The standard that we use in the US is American National Standard for LED components, which are the packages, arrays, the controllers, and the drivers, all of the things that we have talked about very briefly here today. All of these are covered under 8750. CSA has 250.13, which is substantially similar to 8750 because we gave them the copyright to use majority of the materials there. Now, one thing that I want to say about 8750, this standard is not design specific because, as I explained, we have isolated and non-isolated. We have constant current and constant voltage. We have so many different possibilities. There isn't a mandatory design criteria. What we do have is, based on what claims you make and how you have designed it, we have some minimum requirements for safety. Now, with regards to your specific industry, we are at this time working on a standard for horticultural lighting. That's UL 8800. At this time, it's an outline, which is going through the process of becoming an American national standard and also the standard in Canada. We're expecting for all of that to be finished sometimes in the summer. Now, this is the last screen that I have, and I wanted to talk about LED drivers in horticulture applications. Things that you might need to consider is ambient temperatures, likely a little bit higher than what you might expect in a task lighting environment. It's all about correct ratings on the input and the output. Got to make sure that all these pieces are actually appropriate for the power levels that they're operating at. You need to have the proper enclosures because of the environments that you're working in. Today, UL 8800 will only allow luminaires and by extension LED drivers, standalone LED drivers that are rated damp or wet. These are definitions of the National Electrical Code, and it's excluding products that are rated for dry environments. Many manufacturers of horticultural lighting are using remote power supplies on account of the amount of power that they need. There is an issue of cumulative leakages. It's on account of those capacitors that I showed you in those switching supplies. This is not an insurmountable issue. If you go to any type of a information technology environment, they have very similar types of concerns. They have ways to deal with that, but that's something to be concerned about. Let me close with some resources that you might want to look into. We have a site on ul.com with all the different variables that I told you about LED drivers. You can go in. They have drop downs. You can find out what connection method you need, what input supply you need, what kind of is there a specific type of dimming, output ratings, and it will return to you all the manufacturers that have UL certifications on LED drivers with those characteristics that you're looking for. So it's actually a free tool that's available to anyone at ul.com, and it's really quite useful. If you are a UL customer, you have electronic access to all UL standards as part of the service that you receive from UL. If you're not a UL customer, there is a way, and I put in the URL here. It's called Digital View. It gives you limited access. You can look at each of the pages of every standard individually for you to get a flavor of what the standard is about. So that's what I had. Thank you for your time, and let me stop sharing.
Thanks, Bahram. Great talk. What I'll do, let's save the questions for the end. So let's go ahead and listen from Frank, and then the audience can come up with questions afterwards. Let me see here. You have already stopped. Frank, let me unmute you. Just a second. I'm finding you on the list. Frank, can you hear us?
Yeah, I can hear you. Can you hear me okay?
Yes, we can. So if you want to go ahead and share your screen. Perfect. We can see.
Yeah. Everybody can see me, and my mouse is moving. Okay, thank you. Well, thank you, everybody. My name is Frank Cirolia with Artesyn Embedded Technologies. I've been there for about 15 years now, and in the business about 35 years. So this, the presentation is going to be on a different type of architect that hopefully will save energy. And from the numbers, it looks good. So I'm going to tell you the story of how we got there, what we think is the optimal architecture, and then I'm going to do a study case on about an acre of grow land, or inside grow, okay? So I know it's supposed to be about plants, but everybody knows about the internet and the cloud and Amazon, IBM. And if you look at the revenue of these guys, you know, 56% growth in 2017. So the cloud is just taken off, right? A lot of data centers, a lot of power. And it was just growing and growing. And if they didn't do anything, it would just grow to about 4% of the whole US power needs. So in 2006, DOE, Facebook, all these big guys got together and said, we have to do something. We have to bend the curve so that we're not going to eat up all this energy. And they did a great job, from more efficient products to smarter products, both in the power and in servers. And you can see the trend now is fairly flat. So in 2016, they were doing about 1.8% of the total US. And it's about 2% or so now. So they really took it and did a good job about it. So what are we doing about it, right? I think we're going to need to bend the curve also. So basically, in 2012, our industry for legal cultivation was using about 1% of the total US energy. In 2016, Denver alone was using 2%, while the data centers were using 1.8. So this is one state that was using more than all the data centers. So we have to do something about all this, right? So what are we going to do? So what I did is I took that principle of a data center and I said, okay, we have to bend the curve because otherwise it's just going to take off. And it's going to be 50% of the US consumed, you know? So if we're looking at that data center principle, the biggest things that we can do, if you look at the chart here, there's a chart of all the energy that's used for indoor grow. Majority is your AC, keeping everything cool because you have all those lights, and then the lights themselves. So that's the biggest chunk, and that's where I'm going to concentrate a little bit about. So back to the chart here, LEDs. If we move to LEDs, we know they're efficient, right? And that trend is happening already, and that's about a 40 to 70% energy savings if you do for LEDs. And if you compare them to the HPS or that types of lights, LEDs will give you a lot more lumens per watt, right? They're also able to dim down to 10% easily, where the HPS with a special ballast maybe 50%. So here you're saving some energy because you can go to 20% if that's all you need, right? The other thing is the reliability, right? LEDs are going to last 10 times longer, you know, maybe longer than that, really, even though this doesn't say that. But the biggest problem is when you have to get rid of HPS lights, there's mercury in them. And so it costs energy just to get rid of the lights. And if you use HPS or that type of light, you're changing them often. So it really makes sense to move to LED lights. And if you look at the market, it is happening. So and then by 2023, another 31% move to LEDs. And that will continue. And some of these other ones may be just for, you know, home use or, you know, smaller outfits, but LEDs is moving. It's great. Now we have to concentrate on the AC part of it. And that's where I'm going to focus on is how do we reduce the cost for your AC, cost for your input If it's a clean input, utilities will give you a break, right? And we're not using clean input. So that's what I'm going to focus on. So I'm going to talk about a little story on how we got there, okay? And like I said, the goal is going to be to reduce the AC cost, the AC amount, and to improve the input efficiency to save cost. Before I get started, not that I'm plugging products, but I just want to let you a little bit about the equipment that we're going to be using and are using. These are racks, they're basically 19-inch racks, and within it is these modules. This is a module, and they just get plugged into this rack. We have a 24,000 watt and a 12,000. I'm going to talk more about the 24, and then the case study. It has 8 modules. Okay, these modules can be various voltages and currents, but they're 3,000 watts each. So these are 3,000 watt modules. Each module is independent and very smart. So you can set up scheduling, dimming, you can do voltage mode, current mode, you can do analog current mode, you can do a lot that I'm going to talk about a little bit. And actually you can put these in series. There's a 250 watt module. We have a customer using 400 that wants to use 400 watt volt lights. So we're going to put 2 in series, you know. Anyways, this is the equipment we're going to be talking about in these modules, 3,000 watt module, okay. So if we look at what's being done now, is basically every LED chunk, I'm going to put them in 600 watt LED lights, has an inverter, right? That's the typical way it's being done now. And we sell inverters, and that's how we started. This is a Spectrum King lights, and we were selling them drivers, right? And like it was discussed, if you do use drivers, they should be IP65 so they can get wet. Temperature range has to be pretty high. If ideally, you shouldn't be using any fans, but basically we were using drivers. The drivers produce a lot of heat within this area, and that's how we talked to Spectrum King. We were saying, how do we reduce the heat? And that's when there's dawned on us that we should really get rid of all the drivers and move them someplace else. So with the system, one of these racks or one of these modules, each module can handle 600 watt drivers, okay? So if we assume there's 40 drivers because you have one rack, if you look at the losses here, LED drivers are 95% if it's a good driver, right? And so each driver loses 30 watts. When you multiply it all out, it's 1,200 watts. It's 4,100 BTU an hour that you have to handle within a room that has 40 of these. So now if you can put this outside into an electrical closet, you just save this much heating that you have to handle. And what we're finding is, cost-wise, if you're in the 10 to 14 drivers where you're using, say, more than 14, it starts to make more sense to start using this type of system, even if it's the 12,000 watt with a couple of modules, because you'll save, or its payback is fairly quick. You don't have to pay for all that AC that you need. So we went from the drivers, again with Spectrum King, and they were using 54 volt lights then. So one of these modules, it's a 3,000 watt module, was handling 5 of the lights, 600 watts each, right? And since they were 54, there was a lot of current that had to be fed to power these, right? So what they were finding is it was a little rough on installation and a little costly on the wires, right? So after an installation or two, what they decided to do is make 250 volt LEDs. So now with 250 volt LEDs, instead of a 56 amps that you need, you're down to 12 amps. So now your wire size is down to about a 14 gauge. And if you look down on this column here, initially we're using 3 gauge at about $1 a foot, right? And then they went to 14 gauge at 10 cents a foot. And they also saved about 50 watts. This is for about 200 feet, because about an acre is about 208. So this is just, and there's a lot of 200 feet, right? Because you're putting into zones and stuff like that. So, and that's just one module for this. So what we think is the best option is to use some high voltage. Like I said, we have another customer that's thinking about using 400 volts. So, but to use high voltage, putting the DC or the power source in the electrical closet, an electrical closet. Now, this system is all 3 phases. You're going to have nice, clean input. So, besides this being the optimal way of doing it as far as power, so that all that heat is not in the grow area, it's basically an electrical closet that you can exhaust easily. Besides all that, the other thing that you really get out of this is that you don't need a PLC, because these racks, let's say you even have one rack. We have this little box, it's called a power controller, Power Pro communication module or connection module. So you can take this with one rack or up to 6 racks, and inside here you can put in different schedules for different modules. So, excuse me, you gotta be careful of the mouse. So if you have 6 racks, if you have 6 of these, right, that's 48 of these 3,000 watt modules. So you can have 48 3,000 watt zones. And each of these zones can be doing different things. You can have 2 of them going 12 hours on, 12 hours off. You can have some that are starting off at 10%, 20, while the other ones are really coming down, so that you don't have everything on at the same time, you know, so that they think the day is one zone is a day and then one zone is a night. So you can do all kinds of things, because these modules are smart. And you can do it either web-based, so that it's wireless, and then you can get rid of all this PLC and the I/O ports. You don't need all this wiring. So you just saved a lot of money and a lot of energy just in driving this, because it's smart enough to drive itself and to drive the light. So basically, if you had 6 of these, you can have 240 lights or 8 zones that you're doing whatever you want with it, without any of the PLC needs. And that's a freebie. And again, it's centralized, so it's not in the grow area. And if you do use the digital part of it, which is web-based, they have these dashboards, so you can actually start monitoring the input, the modules, you can have cycles, you know, scheduling. You can monitor your iPhone, iPad, and make changes. So it's pretty nice, and that's all digitally and through the cloud. But at the same time, we can also provide the analog signals, 0 to 5, 0 to 10, on the front of the module. So that even if you're monitoring various other items, you can have this monitoring equipment within the electrical closet, and then you're just running small wire or length wires into the front of this for 0 to 5, 0 to 10. And again, either voltage or current you can use. So the modules are pretty smart, again, digital or analog. So really, the solution that we're proposing and that we're actually working with various customers is you put all the power in the electrical closet. You have the controller, so you can either do it through the web, or you program everything here and do it locally. So you have all the schedules that you want. Any of the monitoring, you have local also. The sensors can go out to the various floors, but then you have small drives, small lengths that you have to bring. The input of this thing is very efficient, the power system, and I'm going to talk about that a little bit, because you save a lot of money because it's just the THD is so low. So basically, this is all an electrical closet, right? The power. You run 3 leads, positive, negative, and the chassis, or the earth ground, into these conduits, or these are ND and NUMA junction boxes with the fuses in them. Okay, so they're all fused. And whatever type of plant or other type of floor you have, it works. Okay, so that's our proposal. And this is a case study based on an acre. And that's going to be based on the centralized remote, basically an electrical closet, versus your traditional driver for every LED. Okay, so we're talking about 1 acre. For the 1 acre, and these are using 600 watt lights to make it easy, you're going to need, 1 acre, about 1,763 LED lights, and the total power you need for those lights is a little over 1 million watts, basically. Okay, so for our rack, these are 24,000 watts each. you're going to wind up needing 44 racks. And this is the input to the racks, basically three-phase. Okay. With the drivers, okay, we have this many lights, 1,763. That power, 1 million. Now, you basically need one driver for every light. Okay, so you have 1,763 600-watt drivers that you're going to need. This is more of expense versus efficiency, but there's some of it in there, because here is the price basically if you use these rack systems centralized, the number of racks you're going to need, all the modules you're going to need. It's about 190,000. Okay, using the drivers, you're going to need 1,763 drivers at about 97 bucks. So you're at 171, a little bit better, right? Now for the controls. For our controls, we just need that little black box, the PPCM, and we need one for every 6. So it turns around that we need 8 of these boxes at 120, so 960. For the PLC, and we've talked to customers, and they said we're conservative with this because I question it. For the PLC controller, you need I/O ports, you need the PLC. That's expensive equipment, and it's about 180,000 for that much light, for this many lights. And then on top of that, the wiring. On our side, you don't need the wiring if you're going to do everything digitally. On their side, if you do it, the wiring, it's almost $23,000 and all that wiring that you need to control the light. Now the AC part, right? Because our system's in the closet. The other ones, all these LEDs are in there, the drivers. So you're going to have 1,763 drivers, right? At 95%, basically almost 53,000 watts you can dissipate within those grow areas. And that's 180,000 plus BTUs, which means you need a 15-ton additionally to whatever AC you need before. So that's just 15 tons extra, which is 16,500 just for the equipment and installation roughly. Okay. So basically right now we're picking up a 5% savings by putting in the equipment into electric cars just because of the heat. Okay. And then for the energy part, just plug it into the utilities. Okay. The biggest item here that helps the centralized is the equipment we have is the total harmonic distortion is only 0.8. On the drivers, they're up in the 16%. The utilities pays you on the parent, charges you in the parent power. So when you do the numbers, the parent power using drivers, you're 1.28 kilowatt volts amps, kVA, where the centralized, because of the low THD, you're at 1.156. It's a 10% savings just by plugging it in. And forget about the light and the heat, but just your power and your electrical costs. And that's assuming 10 cents per kilowatt hour. If you're paying more, it's even going to be worse. So basically, the two systems, using the centralized one, you're saving $110,000 a year. And I'm not including the AC yet. If I include the AC, we had the 1 million watts that we needed, and then we had to put in an extra 53 because of the heat, right? So we're 1.1 million watts that we need. And then when you do the numbers, it gets to be about $150,000 in savings because you don't need that AC in there also. So basically, the reason I say it makes sense, architect, is I've had a bunch of booth duty, right? And in our booth, we usually have a lot of LEDs from different companies. People walk by, they look at the LEDs, and they keep looking, and they're looking for the inverter. They're looking, and I say, you're looking for that inverter, right? Yep. So the inverter is in an electrical closet. You know, why put the heat on in the rooms? And a bunch of them, you know, that makes sense. That's why more of that being done, right? So remove the heat, but by taking the drivers out of the grow area. That's about 5% energy savings, okay? And it just makes it easier on the plants, right? And then the input, if you have clean input, and it's also three-phase versus single-phase, so it keeps all the phases equal, so that utilities love that also. Otherwise, you have to do something. So basically, 10% savings in just your input. And then if you can go to higher voltage on the LEDs, you're going to save, we're saying 1.6, but there's a savings there. You're also going to save if you're able to dim, right? Because you don't, even if you use an HPS lights, if you can only go down to 50 and you really don't need 50, you really just pissing power away. So if you can dim, and then additionally to that, you don't have the extra expense for the PLC and IOs and all the wiring you need for that. It makes life easy for all the installation, right? So in summary, if you look at what the data centers did, we have to do something, right? So what are we doing? We're going to LEDs, right? That's one nice thing that's happening. The trend's there. So that's a nice 40 to 70% of energy savings. And then if we can do central power architecture, we can save another 15%. So hopefully this circle will start to be a little more equal, and then we can tackle some other parts of it. But I think if we continue working on going to LEDs and getting the power out of the grow areas and having efficient inputs, I think we will do our parts also. And that's all. Thank you for your time. I'm sure there may be questions.
Thanks, Frank.
Thanks.
Thanks, Bahram,
Yes.
as well. Well, I'd like to thank both of you for the talk, and let's open for any questions from the audience. So let me do that. I did this last time. I will do the same. Everybody is mute right now. I will unmute everyone on the call. So if we have too much noise in the background, I'll mute everyone again, and you can send me questions through the chat. But it works well last time. So let's see. And right, I have unmute folks. Well, yes, I unmute everyone on the call. So anyone has a question from the audience? I do have a few.
This is Bob Hoffman, Shenandoah Growers.
Go ahead,
Can you hear
Bob.
me?
Yeah.
Okay. With the for Frank, the central power supply that you utilize. So we've been investigating the centralized power supply. Is that conversion of AC to DC from 483 phase down to higher voltage DC? Is that a transformer at that point for the syncing for the 483 phase to DC?
It's a power factor corrected front end. So it's a active power factor. So it's not a big transformer.
Okay.
Because it has to be efficient. So the system is about 93% efficient. So
okay.
Everything the rack is basically a big power factor corrected unit. So you get the low harmonics on the input, and the output is the high voltage DC. And then these modules that get plugged in, they get plugged into this high voltage DC, and then they convert it to whatever voltage is needed for those modules. There's, like I said, there's 12, 24, 80, 120, a bunch of modules, a bunch of voltage.
Bob, I think I think what he's saying is that his rack mount unit that he's selling is the conversion from high voltage to low voltage. So you don't need to have a separate transformer.
Okay. And then the question is, when you're on the DC side of that, when you're getting out on the DC side, how far can you go without having a big loss from a drop off from power loss from the distance?
It doesn't matter, especially if you're using current source, right? If you're using a voltage source, then you have to pay attention to the wire size and the length, right? And what you like to have.
Frank, I don't think you're answering the question there.
So so asking is how far are you limited before you have a drop in power getting to each light, or till you have a reduction in efficiency with, I don't care if it's 14 gauge or if it's 12 gauge, whatever it might be, but how far can you go with this from the power source?
You, I would say 300. You can go fairly far if you're using constant current, because it doesn't really care. It's just the current that flows from one side to the other.
I may
you
question
can go
that statement.
hundreds of volts. Maybe I'm not thinking.
Bob, this is Mikhail from TSR Grow. You likely can go about. It depends on the gauge of the wire, but you're going to have some voltage drop across that distance. It's
Right.
depends if you're 10 gauge or 12, or we would typically say 12 gauge if it's 150 feet. For 300 feet, we're looking at 10 gauge, and longer would be 8 gauge. But you're looking at probably a drop at 350 feet at 10 gauge. It's I think somewhere around 7-8 volts. So it depends on your fixture voltage and the current. So those can all be calculated, but it really depends on the run and what you're trying to do in that situation. But you do have some drop.
And for the most efficient power supplies, is this exaggerated? Because most of the times when I've spoken to electrical engineers before, they've told me that you might pick up 3 to 5% gain in efficiency versus your traditional power supply, such as brand names of your top end of power supplies, a 600 watt power supply, you might gain 3 to 5% efficiency if you were going with that direct current. Is that correct, or are you talking higher than that?
Well, if you're talking about, it's not just efficiency; it's the harmonic distortion that gets you. Because what I pointed out was our system is about 93% efficient, where the drivers are 95% efficient.
Right.
The drivers are single phase, and their distortion is pretty poor compared to our 3-phase. And that's where most of the cost is coming from, not from the efficiency. It's coming from that total distortion, harmonic distortion.
Okay.
As far as just a little bit about Artesyn, we're a $1.2 billion company that does 80% of it is power. That's all we do is power. And so we tend to do quality work with, and we know that the input is important in this type of environment, because you do use a lot of power.
Let me switch the question here. Follow up now. Regarding what Frank just mentioned, this new DC power distribution or the centralized power distribution, has UL looked into that, or do you know about any standards or anything that would be related to that, or any barriers for market adoption looking for safety standards?
So I think you're asking that question from me. From our perspective, this is simply another source of supply. And, if it is high voltage and high power, it has certain concerns that you might not see, say, from a class 2 type of a supply. But we have ways to mitigate those. We would make sure, as it was discussed, that we have the proper wire gauges, temperatures are not exceeded. There is appropriate overcurrent protection on each side. Inside the luminaire, now you're talking about a high voltage, high power type of circuit. What kind of access do we have? So if we are presented with something like that, obviously we have in our standards requirements to deal with those.
Yeah, from our side, we just...
If I may,
Sorry.
the system that was presented here is not unlike a data center. It's really a very similar concept. And so it's not something that is, there's a known technology that's being used for a different purpose.
Okay.
As far as our system, it was recognized just because it was designed also for the medical guys, but we just made it listed so it's easier for the growers to get either UL or ETLC. So we do have one grower that already has the ETLC done with it, and there's another grower here in the U.S. that hopefully has finished the UL part of it, That's where we changed to listed instead of just recognized, because it makes it easier.
Sure.
I have a question for our UL representative. Isn't it true that the total harmonic distortion of a system is dependent on the design of the driver itself?
That's partially true. It depends what type of components that you have used inside, but there is also how many are you connecting and how much current you are pumping back into that neutral. So it is a combination, but it does start, the building block is the power supply that you're designing.
So is it in your experience, is it accurate to be able to represent a specific savings of energy on total harmonic distortion between localized drivers and remote drivers?
I really cannot speak to, the calculations that were presented, but I am sure, people who design data centers are concerned about the same thing, and they are looking for ways to reduce the effects of the phase shift and what.
Yeah, we can send you the calculations, so, Excel sheet, so that you can do it yourself also.
Yeah, I guess what I'm trying to figure out is whether what is being represented is a specific product specific thing, or is this more of a widespread approach, meaning DC power supplies in the in remote locations being distributed out to greenhouses over low voltage track or DC distribution systems. Is it the approach that saves money, or are we pitching a specific product here?
I have seen other products that are working from DC type sources. So clearly there is a sector in industry who believes that that's a better approach and more cost savings. Please understand that from our perspective, we are most interested in the safety of the device and assuring that according to its design, it can work properly and safely. I think it's true that there are so many different concepts and different implementations. So I really cannot tell you one is better than the other, though.
Yeah, I was just wondering if you had any experience on whether DC distribution, which is what was represented here in a product-specific way,
Right.
is tending to result in lower total harmonic disturbance.
But that depends on the equipment. So there may be others that are doing that, but hopefully for this big power, because it's not 600 watt or a 3,000 watt power supply. You're talking about 24,000 watt and multiples of those, right? Whatever equipment, even if it's not ours, whatever equipment's there, if it has low THD, then you're going to get savings versus all these drivers that have high THD, right? So that's one thing. The other thing is, by having all that in the electrical closet and not out on the floor, you're saving power there too, because you don't have to use AC power to cool it off. So,
but don't you need that somehow, Frank?
No, I mean, what do you mean? Do I need
you still have an electrical room to cool.
Yeah, but that you can exhaust right outside, right? You don't need. It's going to be a small little room, and you can put in a big fan and exhaust it out. You don't need to really even AC it if you have a good fan exhaust.
Okay. The heat load calculation doesn't seem to change. It just changes where you're removing that heat from.
Yes, but again, if you have a small electrical closet, it's easier to get heat out of that than it is to get out of all those floors. For a small room, you don't need a 12-ton AC to get that cooled.
Yeah, and Jake, I think that's a good question. One, I was thinking about this during the presentation, and I see two different applications here, and it could be more, which is if you're thinking about an indoor farm, so if you're thinking about warehouse or a container, something where it's completely enclosed, having all this heat at a separate room, I think it's a great advantage because now you don't have to worry about the plants and the whole biosystem, ecosystem that are controlling for your plants and having that heat load being part of the equation. Now, if you're thinking about a greenhouse, that's when I was wondering how much benefits can you get out of that, right? In a greenhouse, you're normally using lights during the winter time, it's darker, and this can help to warm up the greenhouse versus having all this heat outside of the greenhouse.
It's only a 5% gain. Yeah, that's why I said the lights are 5%, but the electricity, because the THD is so small, you gain 10% in just the power from the utilities, right? Saving. So yeah, there's two parts of it. And I know in some farms, they actually want, if you're in Canada, they actually want some of that extra heat, right? So it's not for everyone as far as the AC part of it. But the THD is a big part of it because that saves money from your bill every month.
Frank, we're close to 3 p.m. here. I just would like to close with one question. We do have a good mix of growers and lighting companies on this talk here. So really the question is for both of you, for Frank and Bahram. If someone wants to adopt this technology or consider the adoption of a central power distribution technology for a greenhouse or for an indoor farm, what are the minimum requirements, both on a greenhouse side? So if you talk a little bit about the power infrastructure, things like that, and on the LED fixtures, the lighting fixtures, what are the minimum requirements for these two parts of the equations to be able to at least consider adopting this technology?
So on my side, I think we are talking about fixtures that are expected to operate from, say, 250 volts DC and so many amps. Those are likely kind of complicated type of a fixture. You want to make sure that they are rated for the application. They have some type of a safety marking. And also you want to consult someone, an electrician, how that facility will meet minimum requirements, code requirements, because now you're using high voltage, high power cables, not unlike what you do to wire up building, but you need to consider that, have the right wire gauges, connect them properly, things that are of concern for the code.
Awesome. Thanks, Bahram.
And yeah, from my side, it's more of when it makes sense capital expense wise. And like I'm saying, if you're going to use more than about say 14, to be honest, 600 watt drivers within your facility, then you might want to think about going into a centralized location because it starts to get to a point where they're equal in price. And if you're going to have more than 14, if you go through the numbers, you'll find that doing a centralized approach will save you some money. And the bigger it is, the more you'll save.
Perfect. Well, excellent. We are at 3 o'clock here, so I would like to thank everyone for joining the industry talk today. Thanks for your comments. Thanks for the discussion. It's always great to have all these views from lighting manufacturers, greenhouse growers, and our industry experts. So let me thank again Bahram and Frank for providing the talk. And if you have any questions, any follow-up, please send me an email. I'll make sure I can connect with you, with the speakers, and the same from both of you, Frank and Bahram. Any questions, any follow-up with GLASE and our members, please let me know. I'll be glad to make this connection. Just make a reminder again, our next industry talk will be about the CEA market trends and analysis of the 2017 USDA Census of Agriculture. So see how the market is growing around US. And we have our next GLASE Industry Advisory Board meeting in person now coming up at Cultivate. So next month in Columbus, Ohio on the 16th. I look forward to see everyone there in person and just continue the good conversation and the good discussions around GLASE. With that said, I thank everyone, and I see you next month. Have a good day, everybody. Bye-bye.
Thanks very much.
Thank you.
Thank you.
Bye-bye.